Okay, good morning everyone. Today we are going to discuss about the footings. So the footings is mentioned in the IS 456 2000 clause number 34. The details, the whatever the standards we have to take in this clause number 34, it has been mentioned for designing a footing. First of all, we want to know about the what are footings. So footings are the structural members under to support columns and walls and to transmit and distribute their loads to the soil in such a way that the load bearing capacity of the soil is not exceeded, and the excessive settlement and the differential settlement or rotation are prevented, and adequate safety against overturning or sliding is maintained by these footings. Next, so types of footings. Coming to types of footings, there are mainly two types. First is shallow footing and the second one is deep footing. So shallow footings examples are spread, combined, mat footings are the examples for shallow footings. Coming to deep footings, that is nothing but pile foundation or pier foundation. Okay, so these here are the images shown for the shallow footing. This is an animated photo and this is the real photo in the field. Now coming to types of footings. In the shallow footings, there are subdivided into so many types. One is combined footing, isolated footing, strap footing, and strap footing or cantilever footing. These are the some of the types of shallow footings. Now coming to in this, the what is meant by strip footing or wall footing. So the wall footings are used to support structural walls that carry loads per other floors or to support non-structural walls. So throughout the wall there is a footing under the wall. So this is nothing but strip footing or wall footing. Now coming to isolated footing. Isolated footing is for only for one column. Okay. So isolated footing or single footings are used to support single columns. This is one of the most economical type of footings and is used when columns are spaced relatively at long distances. Okay. So this is the image for isolated footing. So this is the another image for isolated footing. So here it is the length, width and the height. Now we are going to this footing reinforcement and these sizes also in the upcoming problem. So now coming to combined footing. So in this they usually supports two columns or three columns, not in a row, or it may be in a row also. So combined footings are used when two columns are so close and the single footings cannot be laid. When two columns are very near, the footings may overlap one on the other. So in that case we can go for this combined footing. Next, these are the images for the combined footings. So next one is continuous footings. So these are the footings support a row of three or more than three columns. They are limited with width and continue under the columns. The width is limited, but the length of the footing is continued as these columns are very nearby, side by side. So here the isolated footing is not possible as when this column footing is overlapping with this column footing, we can go with this continuous footing. Now coming to raft or mat footing. So it consists of one footing usually placed under the entire building area. They are used when soil bearing capacity is very low, column loads are heavy, single footings cannot be used, piles are not used and differential settlement may be reduced. So for this is for multi-story buildings we can adopt this type of footings because due to the heavy loads coming from the floor by floor of a building, and if the soil is weak then we can go for a raft footing which is laid as a slab, how we lay in the top. In the same way slab is laid at the bottom. So this is called as raft or mat footing. So now coming to the second type of footing, nothing but deep footings. These are nothing but pile foundations. Here when the soil is weak we can go for this pile footings. So if the soil pressure has insufficient bearing capacity, then it is necessary to use deep footings such as piles to transmit the loads to deeper firm strata. So wherever the hard rock will be obtained, until that we have to drive the piles and we have to cast the concrete. Okay. So these are the images for deep footings. So now what is bearing capacity? It is defined as the maximum load per unit area which the soil will resist safely without displacement. So if the safe bearing capacity is good, then any construction can be laid. So first we have to check the soil bearing capacity of the particular soil where we are going to construct a building. So again, the bearing capacity of the soil can be found by loading the soil, nothing the settlement, and by dividing the maximum load by the area on which the load is applied. So in this way we can get the bearing capacity of the soil. So now coming to, I have taken the example of square footing. So in this, design an isolated square footing of a uniform thickness of RC column of size 500 into 500. The column size is 500 by 500 and it transmits a load of 600 kilonewtons. The SBC, that is nothing but the soil bearing capacity of the soil is 120 kilonewton per meter square. So use M20 grade concrete and Fe415. So coming to this, there are 6 steps. So coming to the first step, here the size of the footing is not mentioned, only the size of the column is mentioned. So first of all we have to find the cross sectional dimensions, which are nothing but length, breadth and height. So in that, size of footing. So how will we find? We will look into it. So load from column from the given 600 kilonewtons, self weight of footing is taken as 10% of the column load. That means whatever the column load, for that the 10% is added. So the total load will be 600 plus 60, which is nothing but 660 kilonewtons. So with this load we can calculate the area. Area of the footing is equal to total load by safe bearing capacity, as we have discussed earlier. So with that formula, the total load is 660 and the safe bearing capacity is given in the problem is 120. So I have substituted here, I got 5.5 meters square. So this is the area I got. So area of a footing formula is nothing but side square. So area of a footing is equal to S square, which is nothing but side square. So S is equal to square root of whatever the area I have got, 5.5. So with that I got the side of a square footing as 2.34. I have rounded to 2.4. So as it is a square footing, so L will be equal to B. That means nothing but the length will be equal to breadth. So 2.4 into 2.4 is my size of footing. Now coming to the next one, step 2, which is nothing but depth, to calculate the depth. So depth is calculated in 2 criteria. One is the bending moment criteria and the another one is one-way slab criteria. So first we will go through the bending moment criteria. So the depth of footing from bending moment criteria, which was taken from IS 456-2000, clause number 34.2.3.2a. In this, the cross section is at face of column. The maximum bending moment will be at the face of the column, which is nothing but this is the overall footing size and this is the column. So the maximum bending moment will be at the face of the column. At this part, the maximum bending moment will occur. So with this, the bending moment formula is equal to P0 into B by 8 into B minus B square. B means width of the footing, small b means width of the column. Okay. So now P0 means net upward pressure is denoted with P0. So again the P0 formula is column load by area of footing. So the column load is 600 and the area of footing means 2.4 into 2.4, which we have calculated in the previous step. So I got the net upward pressure as 104.17 kilonewton per meter. So with this value I have substituted in this formula. M is equal to 104.17 into width of the footing 2.4 divided by 8 into 2.4 minus width of the column, which is nothing but 500 mm, 0.5. So with this I got the moment. Now coming to ultimate bending moment. So ultimate bending moment means the bending moment which we have obtained into factor of safety. So the obtained bending moment is 112.81 into factor of safety of concrete is 1.5. I have got the ultimate bending moment. So with this I have substituted in the formula D minimum is equal to square root of mu by qb. So I have substituted in the formula. I got the D minimum as 160 mm in the bending moment criteria. Now coming to depth of the footing from one-way slab criteria. So this is the second step. So cross section is at the distance of D from face of the column. So whatever the depth of the footing, it is denoted as small d, it will be at a distance of D from face of the column. So D is nothing but effective depth. So with this, V is equal to P0 into B into B minus B by 2 minus 0.01 D. This is the shear force formula. So with this I have substituted in this formula and I got value because D is unknown here. I have kept it here. So VU is nothing but V into factor of safety. So with this the factor of safety is 1.5. I have multiplied here and I have set as an equation because the D is also unknown here. So now tau C is equal to VU by BD. This is all from the IS 456. So so I have substituted here the VU value, and B is nothing but 2.4 width of the footing, and D is unknown here. So assume percentage of steel is 0.25 for M20 concrete. So with this, from IS 456 from the table 19, I got the value of tau C as 0.36. So I have substituted in this formula, and from that solving this equation, I got the D as 290. So from bending moment criteria, I got depth as 160, and from one-way slab criteria, I have got the depth as 290. So we have to take whichever is more, because we have to go for extra safety, so that the D is considered as 290. Now assume the cover D dash is equal to 60. Then the overall depth will be equal to effective depth plus cover. I got as 290 plus 60, which is nothing but 350. So this is the overall depth, and this is the effective depth. Now coming to design of reinforcement. So this is the formula for mu is equal to 0.87 F by AST into D into 1 minus AST by BD into Fy by FCK. So with this, I have substituted all the values here, and I got the AST as 1702.5 mm square. So with this, I have assumed the bars, as in the footing we know only 10 mm, 12 mm and maximum 16 mm bars are laid. So with this area, I have assumed as 12 mm dia HYSD bars are used. So now coming to how many number of bars to be produced. So with this, number of bars is equal to AST required by area of each bar. Area of each bar is nothing but pi by 4 into dia square. So pi by 4 into, I have assumed as 12 mm dia. I have substituted the 12 here, and I got the area is 113 mm square. Now coming to the number of bars, area required is 1702 divided by 1 by 3. I got 16 number of bars. So with this, I have wrote the conclusion as provide 12 mm dia HYSD bars of 16 numbers of uniformly distributed on both sides of direction in the footing. So now coming to the check for load transfer at base of the column. So from IS 456-2000 clause number 34.4, here the permissible bending stress is given as 0.45 FCK into square root of A1 and A2. So we don't know the A1 and A2. So now calculate the A1 and A2. A1 is equal to supporting area of bearing, that is nothing but B plus 2D plus 2D. Here we can see 2D means what? 2 into overall depth. B is nothing but the width of the column. So I have substituted here, and I got the A1 value as this much. Now coming to A2. A2 is nothing but loaded area of column base, which is nothing but size of a column, which is nothing but 500 to 500. With this, I got the value of A2 as here. So now I am calculating the square root of A1 by A2 to substitute in this formula. So I got the value as 3.8, which is less than 2. But as per IS 456, the maximum value of square root of A1 by A2 should be 2. So with this, I have substituted the A1 by A2 value in this formula, 0.45 into 20 into 2, which I got as 18 Newton per mm square. So but actual bending stress is equal to factor of safety into working load of column by area of column. So factor of safety is nothing but 1.5. Working load of column is 600, which I have converted into Newton. 600 kilonewtons is given in the formula. I have converted into Newtons, and divided by area of column, which is nothing but size of column 500 to 500. I got as 3.6 Newton per mm square. So here the actual bending stress is less than permissible bending stress, which is nothing but 3.6 is less than 18. Hence safe. The load transfer for the base of the column is safe. Now coming to the reinforcement details. With the design details, I have drawn cross section here and the plan here. So here are the footing reinforcement, which are nothing but 12 mm dia HYSD bar 16 numbers in both the directions, in this direction as well as in this direction also. And these column rods are given with the L. So here is the plan. Hope you all understood. Thank you.